Okay, let me try this. Okay, this goes forward. Okay. Well, my name is Deniz. Deniz Kaya from Akdeniz University. First, I want to apologize for a very long title. Today, I'm going to talk about the study of the elasticity of the polypeptide nanogels. But the main idea of this talk, or the purpose of the talk, is a promotion for this technique, which we call microreology. And so I'm at Akdeniz University for I think it's been like 4 years now. So I would like to talk about, first of all, the peptide molecules that we used. And so these molecules, we have used 2 types of molecules. And in this part, there's an hydrophobic chain here. And then on the other hand, there's an hydrophilic part of this molecule. And this is a carboxyl molecule that gives out the hydrogen, and it becomes negative. And on the other hand, and there's another type of molecule, which is also an hydrophobic tail here. And here also an amine group, which takes hydrogen to the molecule and makes this the end a positive part of the molecule. So in this study, we use both of them, and we formed, as mentioned in the earlier talks, we formed a physical gel. Rather than a chemical gel, we formed a physical gel. So how this works is this. So if we, we make a scheme of this, so this is a single molecule like this, and then if we put some, like the hydrophobic chain, hydrophobic part here, and hydrophilic part here, and so if like some multivalent ion is next to this this E3 here, and then it's going to. So since first of all, the hydrophobic parts are going to be away from the water, and hydrophilic parts are towards water. But between this like hydrophilic parts, or the ionizable parts, since there are some like multivalent like cation here, it's going to screen the electrostatic effect, electrostatic forces, and when they are screened, they come together. So with these molecules, one can form a fiber like this. So we have like 2 cross sections of this fiber, and then in this cross section, you can see the inner core of the fiber is hydrophobic, and then the outer core is hydrophilic, and between these like discs, like in the other cross section of the fiber, between these peptide molecules, there are like beta sheet-like hydrogen bonding interactions that makes them, like stay, like next to each other. So these are the main fibers that makes up the gel. And so in this picture, so what I'm not really mentioning is this. We have like positive one and we have the negative one, and we mix them together. So we use, instead of, for example, this ion here, we put E3 as E3, and then this K3, which is this is the minus and this is the plus one. So we put them next to each other, and then there's a multivalent part of the molecule, so that which makes them more stable. But you can make it like with small cations as well. So the next. The SEM picture of a gel like this. Again, this is a physical gel. There's no like chemically cross-linked part of this. And this scale bar here is 1 micron. So it's like this big of a scale is 1 micron here. And, and again, an SEM, so this was an SEM picture, and then there's this TEM picture. And this scale bar here is roughly like 20 nanometers. And the 20 nanometers here corresponds to the thickness of the single fiber. So why do people use this? They use it for these structures to make an extracellular matrix, and they use it for gene and drug delivery, and they use it for supramolecular chemistry, and again, like a gel like this, a polypeptide gel, and then these are the cells that are attached to this matrix. And you can make this like with a collagen, with a natural biopolymer, or you can use this type of gels to, to breed your the cells and do your drug delivery. So the part that we are interested in is this: like, in order for cells, for example, to adhere to this ECM, extracellular matrix, so that the cells will be happy and then they live, they survive, it should have some certain elasticity. And to measure and control the viscosity and elasticity of the gels are important, and that's where we come in. All right. So these are done with, like rheology. I mean, in rheology, you like one studies the behavior of matter under some systematic force. You can examine the structure of the matter by basic deformations. You can measure flow properties, structures, etc. And in a rheometer, commercial ones, you will have like different type of load cells, and like you can have either a fixed rotation or a fixed stress or like force. So basically, this is just to remind people. I'm sure like there are experts in the audience. So if you apply an external stress to a system, it can be a fluid, it can be a gel, it can be an elastic structure, and what you will have is this viscosity. Viscosity is basically the external stress versus, or like divided by the strain rate, and strain is just the amount of deformation. And and this viscosity is related to this G double prime, which is called a loss modulus, basically what you measure from the rheometer. And for G prime, this is the storage modulus, and which is basically an external stress divided by the strain. So in a rheometer, this is the information that you get. You get the part that looks like a solid, and you get the part that looks like a liquid. Again, rheology can be used in gels, polymer solutions, colloidal suspensions. And the main idea is to measure the structure of the material. So for example, this has been done with rheometers, like if an actin biopolymer. So one can have this G and G double prime versus the frequency, or polyethylene oxide solution, again like G and G double prime versus the frequency. So depending on the frequency, you measure different elastic and viscosity constants, which makes sense, what you were expecting. Okay, so our technique is, like this traditional rheometers, measures the average value of the response of the material under applied force. And it assumes, or like it needs the material to be homogeneous. Like when you apply a force, you don't want the material to be like inhomogeneous in some parts, or you don't really know whether it's inhomogeneous or not. And it assumes that the material is homogeneous, and it cannot really reveal the local properties of the material. And the material under the study should be at least 0.5 microliters of the sample. So if the material is very less in quantity, some materials are really hard to synthesize. And so the traditional rheometers cannot be used. And that's where needed, or like we wanted to study this microreality technique, which can overcome this, hardships. So how to do the microreality? This is basically this is an advertisement for, potential graduate students, how I, lure them actually to study this. So it's quite easy, or like simple. You have the material. It can be gel, it can be, like fluid, it can be, any material that you wanted to study. You put colloidal particles in it, and you mix them, and you put the sample under two, glass lamels, and then like you put that under the microscope, optical microscope or fluorescence microscope. You will need fluorescence microscope, and then if you have colloidal particles to be like fluorescence labeled. And then next is you sit and watch, actually. And this is again the advertisement for the graduate students, potential graduate students. And if I want to, what it means to sit and watch is basically the image analysis part comes in. And so you have to find the positions of the particles here. And that's the main idea. And in order to find them, you have to clean the background. And are the particles real? I mean, the human brain and human eye, I mean, we can detect the patterns very quickly and easily, but it is really hard to teach computer to do that. So are the particles real? We have to check this. And we have to fit this Gaussian function to the particle intensity profile in X and Y directions to get to the sub-pixel resolution. I'm going to talk about why we do this. And again, like achieve the sub-pixel resolution. So in this study, like if you work with 100x objective, the maximum pixel that you're going to get will be roughly like 100 nanometers, the pixel size. So we need to achieve the sub-pixel resolution. And we repeat this step for all other particles in the view. And repeat all these steps, all these steps for all the images. So for each measurement, it is roughly like 100 particles and like maybe like 2,000 image frames and roughly like 200,000 steps of doing work. And basically what I tell them, like sit and watch, is basically a little bit of working to do. So the advantages of the microreality is 5 microliter over the sample is enough to get the results. And it is possible to work with biological samples and that are hard to purify or produce, and precious samples as well. And the frequency of the image capture of the camera, that defines the frequency range of the measurement. So if you have, for example, most of the cameras right now can take like 30 frames per second. So that will be your minimum frequency in this case. And then like if you go to like a faster camera, like 1,000 frames per second, that will be your frequency of the measurement. And the main idea of this microreality is that the Brownian motion of the micron-sized colloidal particle in the sample deforms the material passively. What it means is that, like, if you put a colloidal particle, as you all know, like in a liquid, it will do a Brownian motion. So in a rheology or like a rheometer, you put the physical, like external force, by your setup. But like once you put the particle, the colloidal particle in the system, since it's doing this, it's Brownian motion, it's deforming the material automatically. So which means it's a passive. You just like sit and watch and then like measure the position of the Brownian particle. So this is called passive microreality. There are techniques that if you do like an optical trap, and you can just move your particle, or if you can just like put an like magnetic particle there and like apply a magnetic force, you can also like put an extra force on the colloidal particle. So that will be called an active microreology, but in a passive microreology, you just like put the particle and let the Brownian motion do the work, and then you just measure the position. So a microscope and a camera and a computer is what you need, and then in any university you will have a fluorescence microscope, and it will have a camera attached to it, and then all you need to do is like record the data and analyze it. And small volumes are enough. And the Brownian motions of the colloidal particles are due to collisions of the water molecules, that is like pushing them around. And the energy that drives all this is KBT, the thermal energy. And actually the downside of this technique is that we can only measure like soft materials, like we can only measure like maybe like up to 100 Pascal. So this is the superior part of a rheometer, like the rheometer can measure maybe like megapascals, but we can only measure maybe like hundreds of pascals in this method. And also, since you're doing this work under a microscope, you have to be able to see it. It has to be transparent. So that's the only two downsides of this method. So again, the experiment is once you have your sample, you put it under a microscope, you do the image analysis and measure G and G double prime. And we put this E3 plus K3 plus colloidal particles in the test tube. And, and we do this. Let me see whether this works. Yeah. So what we are seeing here is the colloidal particles that are embedded in water. So we want to first check the results from water. What we can measure is the viscosity of water, whether we are measuring it this right. So what we are looking here is the single particles. This is a micron-sized, the colloidal particles here. And maybe like hundreds of particles. This is looped, so. And then you can see the particles are going away from a focus and going in Z direction as well, and then you can see them like in XY motion. So before moving further, I wanted to talk about why sub-pixel resolution and how we do this. And this is also a well-known thing. But under optical microscope, the diffraction limited resolution is depending on your wavelength, and then depending on the numerical aperture of your objective. So the resolution is like roughly like 200 to 300 nanometers. And in our system, 1 pixel is roughly 125 nanometers. And then in order to be able to say that the particle has moved like that much, you have to get down to this, like the fractions of the pixel. So how we can do this is basically, so this is the original image. This is a pseudo-colored image, but this is the real data from the previous slide. And what we see is the intensity of a colloidal particle is, collected at the center. And what we do next is we subtract the background. And once we subtract the background, it's much clearer. And if you do a line profile of an original image, so like an X profile on this, for example, this line, and then the original image has a discrepancy between the background and the maximum point, maybe like so this is like 8-bit image, so like the maximum is like 260. So, but roughly here is 150 to maybe like 20 or 30. So it's like 120 of a bit scale data that you can work on. But if you filter it, the background will be much closer to 0, and you enhance this like with with a Gaussian parameter. So the filtered image will be looking like this, and then once you once you have this image, and then if you put a Gaussian onto this, and then you will see that, so this represents one pixel and this represents another pixel. The tip of the Gaussian fit here will be a sub-pixel position. And that's how we do this. So again, a sub-pixel, like within this pixel, so this pixel is roughly like 125 nanometers, and we can say maybe like 10 to 20%, depending on your system, 10 to 20% of the pixel that we can tell. So we can tell technically this particle has moved 10 to 20 nanometers with this technique. So let me remind you also like the theory behind this. So if a particle is embedded in a fluid, so the forces on the particle will be a random force and a frictional force. And this is called the Langevin equation. And the resistive viscous force is proportional to the speed of the particle, the colloidal sphere. And if you do a Laplace transform, and then if you have, and you get to the velocity-velocity correlation function, and that's what you get, like without any more assumptions. And in this technique, so you have v is the velocity, and if you make a conversion to the position, what we measure is the position, like at a certain frame, and then using the equipartition theorem, and you ended up getting this like position correlation function with this, and Xi is again the viscosity, the frictional coefficient in this case, and due to our technique, so this time that we achieve is much larger, so much larger than m over Xi, and Xi is the viscosity of the liquid. I mean the frictional coefficient, which is related to the viscosity, and since our mass will be a 1 micron particle mass, and this number is like quite small, and the t that we are dealing with is between frame to frame, so like the frequency is much higher, or like the time is much higher than this value. So we are safe to assume, so once you assume this, you ended up getting this, and this is again in one-dimensional result. It's in 2 kt over Xi times t, and again this is in diffusion. So like if this is an ballistic, like if you do this experiment with a very fast camera, like 10,000 frames per second, you might be able to get to the like chi-square to be like t square with a coefficient in front of it, like a ballistic regime. You can also like get to that result. So in here, so this viscosity, or excuse me, the frictional coefficient, from this experiment we measured this, and we all know that, and then we can ended up getting the value of the frictional coefficient, and which is related to the diffusion coefficient, capital D here, and this viscosity is also related to this 2D is equal to kT over 3 pi eta times r, and r is the radius of the particle. So again, we measure this and get this eta value, and and one can also like measure the like from this what we call this one is this position correlation function is actually the mean square displacement of the colloidal particle. So which we call MSD. Wow, I'm too slow. Sorry. Okay. Well, and the fluctuation dissipation theorem, you can get to this G parameter, which is basically at the end of the day, it's like the energy over pi times the radius of your particle. This is your frequency, the 1 over time, and this is your MSD. So once you get this MSD, you can measure this G parameter. And again, like from the track, this is the data, and then a single track can look like this. And then from this, we measure the MSD in 2 dimensions, X and Y. And from this MSD, in the water, the measured viscosity is 88, and then like the literature value is 89. So it's like between 1% and 2%. And in our system, this is our system, and we use like different types of colloidal particles, like different size and different surface structure, which looks like amine and like carboxyl group. And we basically add them and like get the physical gel. And this is maybe if I go to a higher zoomed. So this is the motion of the colloidal particle in a gel network. And you see they don't really go away from the Z focus, and they kind of like stay in the same Z position. And then what we measured is basically if we change the concentration of the gel, then the MSD will be going towards like lower values, which means it gets like stiffer, which you would expect. And then from this MSD value, we can measure G and G double prime for different viscosity. So the input is this, and then the output is this one. So this is basically the main the result. So you have G, and then G is equal to G prime plus G double prime, and then there's the this is the least concentrated, and this is the most concentrated gel that we have. And this is in terms of Pascal, so it's like 1 Pascal is what we have the most time. But when we compare this with a rheometer, the rheometer value is much higher than ours, and we wanted to understand, let me just skip this for a moment. We wanted to understand what's going on. And if you look at like single particle like MSD, we have seen this, that the particles, so this is an MSD data, and then this is the bold one is the average of them, but some particles are much, they have like much higher MSDs, and then if you do a distribution, you see that they don't really, go in a like nice, like in a like Gaussian distribution here, but like we have like very fast particles. So, and if we color code them like in an image, so these red particles are basically the particles that are moving fast, and the black particles or the dark particles are like moving like less. So if we, and then this situation is irrelevant of the concentration of the gel. We have seen them like at different like gel concentrations. We have seen this like heterogeneous distribution, and one can think that maybe like if we sort of like just like put like a triangulation onto this, we can see like hot and like cold patches, and one can assume this, but this is not very true, because what can happen is this, like if we have this scenario, like particles experience the gel network, that's what we want. That's what you measure the bulk viscosity. But if the particles, I mean, once you change the concentration of the gel, if the particles are not, like attached to the fiber network, they are experiencing a microenvironment here. They are experiencing more fluid rather than gels. So that's the one downside of it. So like the hydrodynamic interactions are taking place. So this doesn't reflect the bulk viscosity, viscoelasticity. And then sometimes if there's a specific interaction, for example, between the particles and the gels, then the stickiness of the particles can like measure the tough gel, which is not really true. And sometimes, even if the particle is in a void, but it can attach to the gel, then it can also like measure a wrong viscoelastic coefficient. And again, I'm being the devil's advocate here. So if you look at the SEM picture, not all the fibers have the same thickness. So like the thickness are different as well. So this is also the problem. So what we ended up like concluding is this. Specific interactions are taking place, like the plus and minus, like the opposite, like electrostatic interactions plus, and then like there might be some specific interactions due to like the patchiness of the colloidal particle versus the system, and the charge concentration is a key factor of the stability of this fiber network. Microreology is an easy method to implement, but it gives you amount of like a bunch of like a huge amount of data, and then is a powerful tool to understand the heterogeneous structure of a network. And what needs to be like corrected, this is my last slide, and is that the particles that are surrounded with the fluid, we need to extract them in order to get to the real or like corrective viscoelasticity. And this is a method called like the two-point microreology, like identifying what is correlated or not. And SEM and confocal images can be also like taken to understand what's going on in here. And the concentration of colloidal particles and peptide molecules will be tuned, and maybe like a grafted colloidal particle can be used to get to the least heterogeneous system. Okay, well, this is my group, and thank you for your time.
So we have time for one question. Okay. Microphone.
Yeah, thank you. So you mentioned that at least in the limit, when the size of your particles is much larger than the cavity size in the gel, your calculation of this x square expectation should give you the viscosity of the gel.
Yes. Yeah.
So doesn't that still assume that your particle actually performs a random walk inside the gel, which means that this x squared is proportional to t?
Yes.
I mean, is that justified? I mean, do you see that?
Well, no. Actually, in a viscoelastic medium, you will get the x squared to be related to t in a viscous medium, like a fluid. But in a gel network, it has to be like sub-diffusive region, which is t to the like less than 1. So this is what we have seen in our gel, and again, like that's why I mentioned the Langevin equation, the solution for that, like how you can get like from the MST to the G parameters, which we are doing by fitting and like trying to get
to more complex kind of behavior, which
yes.
you already know.
Yes. Yes.